Good morning, everyone. Welcome to the BEURO seminar series. I'm honored to introduce our today's speaker, Professor Dara Entekhabi from MIT. He will be talking about water exchange in the oil plant atmosphere continuum. Professor Entekhabi received his BS and MS degrees in geography from Clark University in Massachusetts and PhD degree in civil and environmental engineering from the Massachusetts Institute of Technology. He's currently a professor with joint appointments in the Department of Civil and Environmental Engineering and the Department of Earth, Atmospheric and Planetary Sciences at MIT. He's the science team lead for the NASA's Soil Moisture Active Passive mission that was launched January 2015. His research includes terrestrial remote sensing, data assimilation, and coupled land atmosphere modeling. Professor Entekhabi is also a fellow of the AMS, AGU, and the IEEE. He's also a member of the National Academy of Engineering. So without further ado, I will hand it over to Dara to start his talk.
Okay, so you can all see the screen. First and foremost, thank you so much for the invitation to give the seminar. And I really appreciate it under the circumstances to have this everyone log in at this time. So what I'm going to talk about is basically a few questions basic questions in how the water cycle works in the climate system, in the Earth system. And I'm going to organize the talk into addressing very briefly these four questions. So the first question is, how are the water, energy, and carbon cycles linked over land? The keyword is linked. Water, energy, and carbon cycles are the three fundamental metabolic cycles of the Earth system, and they determine climate and the distribution of climate around the globe. And the question is, how are these three linked? We link them in models, in climate models, in Earth system models, but are they linked properly? And what's the consequences if they're not linked properly? The second question is that I'm going to be talking about a new data set from a satellite mission, which measures the state variable of land surface hydrology, namely soil moisture, which we hadn't had before. And the question is, if you bring a new data type, not just more data, but a new data type to a discipline, can it and should it and how can it spur rethinking of our conceptual frameworks? And third, question three is looking at vulnerability to climate change. And the basic question is that, are the regions with the largest climate forcing variability and change necessarily the regions with the largest land surface response to climate? And lastly, the role of vegetation in the water cycle over landscapes. What is the response of vegetation to pulses of water availability due to storms? Do they rehydrate after these events, or do they grow these after these events? When, where, and how much? And can we observe those? So the talk is centered around this mission that was launched in 2015 by it's a NASA mission, Soil Moisture Active Passive. Obviously, it's a soil moisture mission. It was designed and optimized to make that particular measurement. And the four questions can be sort of grouped under observed water exchange in the soil plant atmosphere continuum. I'll be presenting, but obviously this is the work of others. These are some of the current students and postdocs and some of the alumni of the research group that have moved on to other universities. So Roosbe and Dan on the left are current postdocs. Andrew just graduated last week. Alex and Kagan on the top right recently graduated. And Guido Salvucci is a former student from long ago, but now he's a colleague. and he spends a lot of time together. And we have a collaborator in Portugal, Isabel Trigo, who's brings in another data set, satellite data set to the table, and we collaborated with her, and you'll see the contributions as we go along. Now, in all the slides, I don't necessarily give the citations because it's too much clutter, it's too busy. So what I have for the record in the backup section is a bibliography of all the work that these folks have done. So the SMAP mission, again, this was something that was designed and optimized to make this particular measurement, soil moisture, and it's operating in very low frequency microwave L-band. That's near where the cell phone communication is. So it can penetrate the atmosphere, clouds, rain, and some density of vegetation short of tropical forests. It has the radar and the radiometer. The radar failed very early on. That instrument was designed to give us resolution, but it's less sensitive than the radiometer. The radiometer is coarser resolution, but much more sensitive to surface soil moisture. And the mission has a very large rotating light mesh antenna in order to gain this resolution. And that is scanned at about 15 RPM to give us a large swath. So we have a 2 to 3 day revisit. This mission has a set of 5 high-level program requirements. So these are in our contract with NASA to deliver on these science and application questions. And the first one, as you see in the title, is one of the questions that I put on very early on. How are the water cycle, energy cycle, and carbon cycles linked over land surfaces? And measuring soil moisture also has some applications that are long-standing. For instance, flood guidance for flood forecasting and drought monitoring are 2 applications which use soil moisture information, have been using it for decades. These are operational activities, obviously. And but the soil moisture comes from soil moisture accounting, a model. So this is, for the first time, we have a direct measurement of the quantity that we have been modeling all along. So let me just jump in and look at this first questions up here. How are processes that link the 3 main metabolic cycles of the climate system work together? The way I sort of see them working together is that they're like gears in a clock. They turn together, but how they're linked together, the closure relationship between them, basically the diameter of the gears and the size of the cogs, these are what we parameterize in models. Now, when the 3 cycles are linked, perturbations in one transfer to the other cycle and can feed back as well. So if we don't parameterize these closures and link these 3 gears together properly across models, there'll be a major source of uncertainty in how we project climate into the future and perturb one cycle and see how it affects the other cycles. So let's get a little more quantitative than just a diagram of the 3 cycles as gears, and reduce a Earth system model of these 3 cycles, which is usually thousands, if not tens of thousands lines of code, into 3 basic 3 lines of equations, just to see how fundamentally they're coupled together. So the water cycle is a change in the state variable soil moisture. The input is precipitation, and the output is evaporation. So this is evaporative fraction, which is the fraction of the amount of heat used in vaporizing water relative to how much energy there is to do that. So this is a number between 0 and 1, dimensionless. So this is the water balance. Since this term is a vaporization of water, it also appears in the heat balance, energy balance. So this is the change in the heat content of the surface, input energy, the same as up here, minus the sum of the latent and sensible heat fluxes, the vaporization of water and the heat loss associated with that, as well as the conduction of heat. And then there's the carbon balance, which is says that the biomass is proportional to how much evapotranspiration is happening, but translated into carbon. So there's a water use efficiency, which is just the ratio of the carbon flux to the water vapor exchange. So this is the photosynthetic process creating biomass. And then there's a loss of biomass over time. So these are the three cycles, and they're linked together through these functions, the evaporative fraction and the water use efficiency. Now, these depend on the state variables like soil moisture as well as temperature. And the question is, how are they linked? And how do different models make them link together? So again, this is just a three-equation version of what is thousands of lines of codes in an Earth system model. So here's how they're linked in a few sample Earth system models from, doesn't matter which centers these are from. These are just from SMAP 5 collection of model outputs. And taking over a piece of real estate, looking at how this evaporative fraction as a function of soil moisture, this closure function, and this water use efficiency, how they're linked across these six models or six models across this region. So this is the closure relationship that's built into these models in those many thousands of lines of code. And what is clear is that there's large variations across these models in how they link the water, energy, and carbon cycles. And this leads to a large uncertainty in our climate projections of how perturbing one cycle affects the others. This is the statement of the problem. So in order to make progress in this arena, what we need is a benchmark data set of this emergent behaviors based on purely observations. We can't use models because that would be trying to pull ourselves up with our shoelaces. So it has to be observationally driven evaporative fraction and carbon flux, and observationally and independently derived soil moisture on the x-axis. So one other point I need to make is that these parameterizations are put together by sort of taking pieces off the shelves and linking them together. And this is not necessarily how they're going to work well. And these are regarded as benchmark emergent behaviors for which we need the benchmark data sets. So in order to get independent data sets for the x and y axis of those plots, for the x-axis, we have the soil moisture measurements of SMAP. For the evaporative fraction and available energy, we have weather stations and a technique to derive those energy balance components from them. And for the carbon flux, we have a unique other data set, which is satellite measurements in a very narrow spectral band, which overlaps with the fluorescence due to photosynthetic chemical reactions. So it's measuring photosynthesis and biomass development directly. So we have all the elements of the of making these plots, and really it's a lot of work, but the result is one benchmark data set. So this is evaporative fraction from the weather stations. This is soil moisture from the SMAP satellite for these regions across the US, representing different vegetation and climate. And we see a two-regime behavior with a clear soil moisture dependent threshold, where when the soil is adequately moist, you have the energy partitioning being energy limited, so it's independent of soil moisture. But at a certain threshold, the strong water limitation to the latent heat flux occurs. The slope of this is the degree to which the water energy cycle are linked. It's the strength of that linkage. Now, same thing with the carbon flux, the solar-induced fluorescence, which is a direct measure of photosynthesis versus soil moisture. We see the same two-regime behavior, but the plateaus, the sills are different depending on the vegetation type. That's their, in a sense, intrinsic capacity to assimilate carbon. And if we look at water use efficiency, this is landscape or water use efficiency. This is per unit area of land. This is leaf level. This is per unit leaf. And we see a very strong hyperbolic behavior. This is inset is for the entire range, 0 to 0.5. This is just looking at this bottom section of it. So it's very much indicative that when the plant becomes stressed, it becomes much more efficient in its use of water in creating biomass. And this is something that is mapped here using the satellite and station data. But this has been observed in laboratory chambers. So these are, there's a long tradition in plant physiology of taking plants and crops, putting them in a chamber in a laboratory, and then stressing them to see what the water use efficiency response is. So in these chambers, we get the same hyperbolic behavior, but now we can look at it across landscape and in the natural setting. So that's the first question, which is how are water, energy, and carbon cycles linked over the landscape? And I think we are approaching to having a benchmark, purely observational data set to put them climate models to the test. So the second question is, okay, so the soil moisture observations are new. We haven't had them before in hydrology. In hydrology, we usually think of the landscape as a black box where precipitation is input and the runoff and evaporation are output. And the state variable soil moisture was just a sort of internal accounting. No one paid any attention to it or even expected that across models that there would be any consistency in the level of soil moisture. But now we suddenly have the measurements and mapping of the evolution of soil moisture fields globally. So what does that do to our models and conceptual frameworks, those input-output traditional models? Now, soil moisture itself doesn't have a scientific value like evaporation or runoff would. None of those have sort of direct applications. But soil moisture is indicative of how internally hydrologic processes are linked and how they transition across these regimes, like we saw, the water limited and energy limited evaporation regimes. These are very nonlinear processes because you're going across a threshold and you get a totally different behavior and regimes. So let's look at what measurements show us. This is from SMAP. This is time series of soil moisture for a location, an example location. And these are the measurements over time in volumetric soil moisture units. So every time there's a precipitation, the soil moisture shoots up, then it drains and evaporates. and then there's another precipitation event, it goes up, and then there's a long dry down, there's another precipitation event, and so forth. So this is the time series of the state variable of the system. What can we glean out of just looking at these time series about hydrologic processes and how they're linked? So let's do what one should not do, which is take the derivative of a measured signal, because all you do is amplify noise. But let's just try it and see what happens. So if I take just the time derivative of the observed time series, I get the time series in this inset. So during dry downs, like this dry down, I get a negative increment occurring because soil moisture is consistently going down. It goes down a lot faster at the beginning, and then as it further and further dries, the rate at which it goes down reduces. And then you have a precipitation event, which is this red spike. It's a very punctual and very short duration rise in soil moisture, and then you have another dry down, and then another rain event, and so forth. So these are the negative increments and the positive increments in this time series. Again, just purely based upon the time series. And if the time series is statistically stationary, meaning that the landscape is not indefinitely gaining or losing water, it's just going up and down in its water content, then the distribution of the blue and the distribution of the red should have the same central tendency or mean. That means that there's as many, if I accumulate all the red and if I accumulate all the blue, they should add up to 0. They should be the same. And on the right-hand side here is the probability density function of the blue and the red. And obviously the means are the same because it's statistically stationary and the landscape is not indefinitely losing or gaining water. But the distribution around this mean are very different. Is there something to be learned from that? And of course, you have this all over the globe. So it's not just this one pixel. So we're trying to see what can we learn about the differences in the distribution, even though the means are the same. So let's look at it again, but isolate one of these dry downs to see what's going on. So this is, let's take this dry down and plot it down here. So it's just one event following a rainstorm. After the rainstorm, soil moisture jumps up and very quickly drains to the field capacity. So this is drainage under gravity to a field capacity, after which gravity drainage becomes much, much smaller. So this is well known, but the rate is very high. And then once the drainage sort of diminishes, the losses are dominated by evaporation. So from this field capacity to that threshold, which we transition from energy limited to water limited evaporation, there is a sort of a straight line. The rate of evaporation, the rate of loss, water loss, is constant. It equals to the potential evaporation, the available energy. And once you hit this threshold, now you have water limited evaporation. So the soil moisture is reducing the evaporation rate, and the drier it gets, the more it reduces it. So the rate becomes variable and smaller as time goes on during the dry down. If I plot the slopes of these as a function of soil moisture, then the from very wet to field capacity is the drainage process dominating, and it's very high rate of loss. Then during the between field capacity and the transition, evaporation loss is limited by available energy, so it's potential evaporation, just one number essentially for the loss. And then after this, and this is stage 1 or energy limited evaporation, a wholly different hydrologic process dominating. So we are transitioning to entirely different processes. And then after you enter the stage 2 or any water limited evaporation, then there's some sort of a lesser loss rate or evaporation below the potential. So if we say that the loss is just the change in soil moisture over unit time between satellite measurements, then this function, loss as a function of soil moisture, is just a conditional expectation of all the data on soil moisture. So you can get this curve, which is essentially pieces of this loss function, purely from the data and without any models. So you can do this across the globe, obviously. And here's an example of doing it over the US, just so that we can focus on things, but there's a wide range of climates and vegetation. So this is how often are we in this regime, in this second stage 1 evaporation regime, or these are 3 different hydrologic regimes during this dry down events. So this is just maps of percentage of time in each of those regimes during the several years of satellite measurements. So the Southwest, obviously, and the West are a lot more in the water limited regime. Then there's this energy limited regime, which is dominated in the more humid regions of the country. And then curiously, there's this drainage dominated regime over the upper Midwest, where there's actually a lot of trial drainage in agriculture. So this maps looks like, okay, you know, what we would have guessed where these regimes are, but these are observational, purely observational. And now we have to ask our models, do they show the same transitions between hydrologic regimes as observations indicate? And also, if we sort of classify which of these regimes are present or co-present during dry downs, we get an average climatological map like this. But then this is satellite data over different years, so we can look at how these regimes move from year to year. So for instance, this is 2015, 2016, 2017, just as an example, but you have these over the entire time series. And these are the boundaries of 2015, just to see how things move. So you see regions switch altogether from being dominated by one hydrologic process to another. This is the well-known flash drought of the upper Midwest in 2017. You see these things moving. There's a wealth of things to see in these maps and other maps that I'm not showing. This is just summary, just from observations. So we characterize this loss function as just the negative increments during dry downs and took the conditional expectation of it. Wouldn't it be nice if we could actually break this loss into what's going on in terms of hydrologic processes during each of these regimes? So the loss is evaporation and drainage. The drainage in red is that sort of drainage to field capacity is very high at high soil moisture, and then it rapidly goes down and it diminishes near some field capacity. We don't know where this is. This is just a conceptual plot. And then evapotranspiration has this 2 regime behavior, the energy limited and the water limited. And you sum them and they become the blue. So this this figure is really the sum of the red and the black. So how can we partition the total loss between these two? So let's just do a very simple but very flexible conceptualization of these. So this is the evaporation. We can, the evaporation loss as a function of soil moisture is a two regime, energy limited, water limited. And let's say that we just define a mathematical function that has this sort of two regime behavior. It can move left and right depending on parameter B. It can move up and down depending on parameter A. This function, depending on A and B, allows this two regime behavior to be anywhere in this 2D plot. So we're not saying what A and B should be, but all we're saying that there should be two regimes with a breakpoint somewhere in this 2D space. And same thing with the drainage loss to the field capacity, just like unsaturated free drainage, we pose a model that's hyperbolic like this. Depending on C and D, it can be anywhere in this domain. And then we say, okay, we are observing the state variable. So that's the black dots, the soil moisture time series. If we bring in precipitation from another satellite, the global precipitation measurement mission, and make the a sort of a cost function, which is the sum of all the SMAP measurements, brightness, temperature, implies a certain soil moisture, and then adjoin a water balance with these loss functions and estimate parameters A, B, C, and D, and let them be anywhere they want to be in this 2D space. So basically what we're doing is we're trying to, instead of soil moisture being a sort of internal variable in a hydrologic model, which traditionally had been ignored, just input precipitation and output runoff or yield, we say, no, let's turn the whole thing around and actually adhere to the state variable dynamics. So we're turning the model inside out, saying, I want to track the state variable dynamics, and whatever fluxes come out of it are the fluxes. So this is what you get once you, in this variational scheme, estimate A, B, and C, and D. The total loss is the black line. So it resembles this state variable run through the loss functions. But now we have partitioned it between drainage, blue, and evaporation, green. They sum to the black. So the drainage obviously is only during the wetting events and very punctual, the runoff. But evaporation is more enduring during the dry down periods. And it has this stage 1, stage 2 behavior as well. The parameters as estimated are here, but we really don't care what the parameters are. We care about what fluxes they imply. So this is the evaporation in millimeters per day implied from this scheme. Again, the input is 2 data streams only. One is precipitation from the global precipitation mission and soil moisture from the SMAP mission. And this is the drainage runoff. And incomplete and unsatisfying as it is, comparing such mapping measurements to point measurements or basin stream flow measurements over the US. These are all the AmeriFlux flux tower data. So these are point measurements of evaporation using eddy covariance instruments versus what this map shows. It's about 70% explained variance. Again, there's a mismatch of what a point measurement is and what the spatial measurement is. And each one has its own estimation error, but 70% explained variance. Runoff is a little more tricky because stream flow has got impediments, dams and hydraulic structures and diversions. But what you have is also around 70% explained variance, but the slope is close to 1. And this is lagging it by a month just to see if there's a sort of a serality issue. But what that allows us to do is then look at the partitioning of the precipitation into evaporation and drainage over all the basins over the US. And they're quite variable across the US. Again, this is observations only, precipitation and soil moisture. And really what this is conceptualizing is that this is the time series of soil moisture, which has a certain marginal distribution, PDF. And these are the loss functions. And what really you have is a derived distribution. That is, these loss functions with this probability distribution function for the independent axis. For this particular pixel, just remember these numbers. It's about 3/4 evaporation, 1/4 runoff in this particular location. So again, this PDF and derived distribution of this loss functions gives us these numbers. So let me just put that PDF on its side to make it look more like a derived distribution. So this is the PDF. These are the loss functions. You integrate these functions with this PDF, and you get these 3/4, 1/4 numbers. So now we can ask questions. What if I change precipitation just amplified by 25% in the historic record, or decrease it by 25%? That shifts the PDF up and down relative to the normal. And you see the impacts on soil moisture above normal here, below normal here. Black is normal, perturbation is purple. Now the partitionings change, but they change different than 25%. So there is strong nonlinearity in this derived distribution because these functions are nonlinear, and shifting the distribution left and right activates different amounts of each. So now we can look at the historical time series. We have precipitation. Instead of just artificially saying 25%, let's look at the historic record and see what the partitioning changes are in the historic record. So total precipitation must sum to the red and the blue, drainage and evaporation. So another way of visualizing this is that each year has a different PDF. The loss function is the same. So we can get the cumulative density function over all these years, 1948 to 2018, where we have precipitation measurements or estimates, and we get a CDF of the runoff. So this is the traditional yield cumulative density function, the sort of annual flood or annual runoff, actually, in this case. But we have it for evaporation and we have it for drainage. How well do these match observations? We did this for a lot of hydrologic units, HUC units across the US. I'll show you the worst one and the best one as sort of the end members. This is the worst one. So this is runoff in this HUC unit and SMAP and estimates. So obviously there's a severe mismatch between the two. As a result, the CDF don't clump close at all over these many years. But in the other extreme, there are situations where they match each other quite well over these many decades of observations. So this is the runoff CDF over 1948 to 2018. When you look at these are the two end members. When you look at which regions do well and which regions do worse, one thing you notice is the regions where it's snow dominated, like this basin, they do a lot worse than this basin, which is not necessarily snow dominated. And that's sort of partially understandable, doesn't explain everything, every mismatch, but we didn't account for snow at all. So it kind of makes sense that that's one major source of error. And I just end this with, now that we have 1948 to 2018 maps of evaporation and drainage, we look at the variance of these over the years. So this is the forcing variance, precipitation, over those decades. This is the variance in evaporation. This is variance in drainage. I have no idea what these mean, but they're intriguing and a lot of food for thought in the future. Again, this tile drainage business shows up, which is curious. But there's so much to see and explore in just having 40-odd years of drainage and evaporation map variance without a severe model. The last thing I'm going to talk about is a very basic question, which relates to climate change. Is regions with the land surface response variability proportional to where there is more climate forcing variability? So the more climate forcing variability, like precipitation change, are those necessarily the regions with the largest surface response variability? Surface response is those water, energy, and carbon fluxes. So basically evaporation is the link between them. So we want to know how much evaporation, which affects water, energy, and carbon cycles, how do they change with climate forcing variability? So this is a mapped version of it. This is variance of annual precipitation over Africa. And this is, if we had it, the water, energy, carbon fluxes or evaporation variability. We want to know how these map together. You know, is it a strong slope or a weak slope, and why? And this was inspired by the work of Peter Eagleson, who passed away earlier this year. One thing he showed in a series of 7 papers in Water Resource Research, one single issue, a remarkable contribution to the field of hydrology. He showed that if you look at storm interstorm periods, the dynamics of soil moisture during these periods, like we've been looking at, not only explain what's going on at the weather scale, but it also explains interannual variability in those. This is, again, runoff recurrence interval, so, or CDF. So what he showed was that interannual variability of water yield can be deduced by assembling statistics of storms and this weather scale intrinsic landscape response during storms and interstorms. So you can build up from storm into storm behavior what's going on in terms of interannual variability. So we'll do the same. We're looking at Africa, and you'll see why in a second. We don't have measurements of evaporation, but we know that during interstorms, when the soil moisture is decreasing, you go from water energy limited to water limited evaporation regimes. When you go across that threshold, the signature of that transition is evident in the surface temperature. This is diurnal cycle of temperature. So you see that where the regime change occurs. So we don't have evaporation, but we know where the regime changes. And just to sort of make sure that this is a reasonable assumption, this is at a FluxNet in Zambia. This is evaporation fraction, the black, as a function of soil moisture. You see the 2 regimes reminiscent on the right. So that's the. Now, the reason why we picked Africa, and we have our colleague in Portugal, Isabel Trigo, as a collaborator, is that she manages the data from a geostationary satellite that is sitting directly at the equator and fixed position over Africa. So it's a wealth of data over Africa. And from their data, we can deduce surface temperature. So we estimate the soil moisture threshold using that data combined from the two satellites. But more importantly, we estimate the fraction of time that we're in one regime or the other. So this is the fraction of time in the water limited regime, 1 minus the energy limited regime. And the conceptual framework is, again, a derived distribution. This is soil moisture. When you're above the soil moisture threshold in the energy limited regime, the energy balance is not affected by soil moisture. But once you go below the threshold, as you get drier and drier, you reduce evaporation and you increase the surface temperature. So the temperature goes up. Now, what is the landscape response overall? Is the PDF of soil moisture with derived distribution over the response. So we go back to this map of precipitation, map of response. What makes one go to the other? What affects it? So this is the same axis as before, precipitation and interannual variability from over the period of record. And this is the sort of proxy evaporation variability, landscape response in water, carbon, energy fluxes. And if we sort this by fraction of time spent in the water limited regime, we get a strong exploratory variance. Again, a weather scale phenomena, the fraction of time spent in water limited regime in interstorms explains vulnerability in interannual variability. Very quickly, the last thing is to bring in vegetation. Question 4, when you have a pulse of moisture, like rain events, what do vegetation do really in response? So this is the drydown in between storms. So these are what satellite is measuring. So one thing that the SMAP satellite allows us to derive is not only soil moisture, the volume of water in the soil, but also amount of water in the vegetation. So the density of water in the vegetation. So we have simultaneous global fields of soil moisture and vegetation. How does water move during the interstorm based upon observations alone in the soil vegetation atmospheric continuum? So this is a time series of the two, soil moisture in blue, vegetation water content in green. We isolate the dry downs. So these are the red dots are consistent dry downs. I isolate them here individually. Sometimes the soil moisture obviously always goes down. Sometimes the vegetation goes down as well. Sometimes it goes up. And actually, it's state dependent. When the initial conditions are wet, the vegetation water goes up. When the conditions are dry, it goes down. And this is just a visual example, but quantitatively, we can see that behavior, state dependence, by looking at the phase plot of vegetation water content and soil moisture. So we take out the time variable. So these are just these same things plotted as phase, progression through time. As the soil dries, the vegetation takes up water and then it loses water. It's not a very convincing graph because it's just so few lines, but it's a satellite. So we have thousands of pixels and many, many rain events. We group them together for these sort of ecoclimatic zones, different types. And now we have a lot of these noodles, and we can sort of make little boxes and average them so that we visualize them despite the overlap. So this is the same graph, but now cleaned up so that we can look at the intrinsic behavior. So what we see is when the soil is wet and it dries, vegetation gains water at a certain rate that depends on the soil moisture and the vegetation water content. And then there's a wilting point after which it crashes. So we can detect what this wilting point should be and what the rate of water gain is during the early dry down. Different ecosystems have different behaviors. Again, this is just an example. You can stare at these and really learn a lot about plant and various vegetation adaptation to water stress. This is the slope mapped over these two regions, and this is the threshold where the wilting occurs. In atmospheric Earth system models now, they usually take this to be 1.5 megapascals as a fixed number. And we see that it's actually, there's a distribution of it which matters and depends on soil type as well as vegetation. Let me just skip to the end. So these are the 4 questions that we posed. One was on how the water, energy, and carbon cycles are linked, what the new data type allows us to do in rethinking our conceptual frameworks in hydrologic models, which regions are more vulnerable to climate change and why, what's the driving underlying mechanisms, and how do plants respond to pulses of water. And again, what the goal was to make it as much as possible purely observational in order to create benchmark data sets for these emergent behaviors in models. So one by one, conclusions is that we can derive observation only based closure functions between water and energy cycle, the evaporative fraction, and the water use efficiency, the water and carbon cycle linkages. And these are benchmark estimates of the aggregate behavior that climate models should adhere to, which they don't right now, and that's a major source of uncertainty. For the new data type, we can conceptualize this now that we have the state variables, that hydrology is really a derived distribution problem with the soil moisture state variable as the distribution and the response functions as how the system depends on those state variables. In terms of interannual variability and vulnerability to climate change, different landscapes have different sensitivities to precipitation variability, climate forcing variability, and what determines their sensitivity is actually this intrinsic property that's evident in interstorm events. So at the weather scale, but they determine the sensitivity at climate scale as well. And vegetation respond to pulses of water, not just average amount of water in a season or precipitation in a season. It actually matters. The intermittency matters quite a bit. There is rehydration and growth going on during the interstorms. And if the storm patterns change, that will obviously then have an implication for what the landscape carbon balance is and how much water in total and carbon in total the landscape exchanges with the atmosphere. So I leave it at that. Again, for the record, this is the bibliography of the work that I drew from in this talk, and it's in the backup. Thank you.
Thank you very much, Dara, for your interesting talk. So I see several questions in the chat box. Let's start with Catherine. Catherine, would you like to unmute your mic and ask your question?
Hi, yeah, thank you for a great talk. It was quite understandable, not easy to communicate these ideas. Yeah, I have the questions in the chat. I'm just interested, when you're looking at various different satellite data streams, I mean, is there a problem with the fact that these satellites don't always pass over at the same time? So you're getting, like a data gap that limits the assessment?
In general, you're absolutely right. That's a major problem, merging multiple satellite data. They don't have the same orbits. They don't visit at the same hour. But in this particular case, where SMAP had its orbit, whatever the orbit sampling is, we are matching it with a geostationary satellite, which is making measurements over Africa only, in this case, round the clock. So there's always a match, but not global, but over Africa. That's why that particular case study was Africa alone. And when matching it with GPM, GPM is actually a constellation. So they have more sampling than SMAP. So we only match them as needed. So in general, you're absolutely right. But in this particular case, we were lucky that it was pairing it with a geostationary and a constellation.
Okay, and then just one other quick question was, what about thick canopy? When you have areas with thick canopy, is it difficult to get these measurements?
The SMAP L-band measurements, this is 21 centimeter wavelength, so it's much larger than typical leaf and all that. So it penetrates some vegetation, but as it penetrates the vegetation, it loses sensitivity. Yeah. So the retrievals over a very dense vegetation are more uncertain, but there's still a signal in there. Okay, and so it's just a degree of uncertainty that goes up. And you really have to get into like dense tropical forests to lose the signal below the noise, to make the measurements signal to noise ratio sort of unacceptable.
Thank you.
All right, next is Zhang. Zhang, would you like to ask your question verbally?
Yes, this is a great talk. Thank you for giving this wonderful summary of SMAP and the measurements. My question concerning the co-variability of soil moisture and vegetation water content during the dry down. This is really cool. I have never seen that before. So I'm wondering, have these measurements used to inform weather forecasts for the coupled with land atmosphere like weather model and the climate model?
Okay. In terms of weather models and operational weather forecasts, they don't have a very sophisticated, they don't need a very sophisticated vegetation model because they only do 10-day, 14-day forecast, very short term. But they're very sensitive to soil moisture because that determines the surface energy balance partitioning and surface temperature and the boundary layer humidity, boundary layer temperature, and so forth. We've been really trying hard to work with them pre-launch and post-launch to incorporate soil moisture in their weather forecasts. It takes time because you can't just introduce a new data stream. It might degrade your forecast, in which case they're liable. So they're doing it offline. And if they see consistent improvement, then they'll switch it online. Okay, but it's a long ways to go. In terms of climate models, what we're trying to do is to create benchmark figures like evaporation fraction versus soil moisture or water use efficiency versus soil moisture, so that models that have tons of parameterizations interacting with each other and have an emergent behavior, are they doing it right? There is no one single line of code in Earth system models that says evaporative fraction as a function of soil moisture or water use efficiency. It's spread across many different little components, but the end result, the emergent behavior, should be that observational graph. That's the use case in Earth system models.
Okay, thank you.
All right, Michael, you are next. You are welcome to ask your question.
Yeah, thank you. Excellent talk. I really appreciate sharing your research with us. My question really has to do with trying to partition out the ET portion from the recharge below the 5 centimeter depth that SMAP is interrogating for the most part. Is there, other than just using the L4 product and trying to get down to 2 meters, is there some other way that to try and back out that recharge portion? And this kind of plays into Deb Mioji's question on root dynamics and things like that.
Yeah. Let me, this issue of, in my backup slides, because it always comes up, you know, are you just seeing this top 5 centimeters or are you seeing more? Do you need to go to a data assimilation product which introduces a model, which a lot of times we try to avoid depending on the use case? And, you know, this sensing depth is a characteristic length scale of emission, and the radiative transfer relationships for that are well known. It depends on wavelength and the amount of moisture in the soil, so the refractive index. So this is the characteristic length scale, which is 5 centimeters nominally, is this. The hydrologic length scale is where the dynamics of these moisture waves dampen out. It's a different number. The question is, what is the link between these two? And if you look at observations alone, this is a depth versus time. You see these waves that determine the hydrologic depth. So, you know, you see the wetting and the drying and different penetrations depending on the average soil moisture. So the question is, if I sense within the emission depth, how much of the hydrologic depth do I know? They're linked together. It's not like the surface and the subsurface are uncorrelated, and there's no information cliff at 5 centimeters. And, you know, we did a couple of studies actually on these 2 different methods. This is based upon purely observations at these locations. So if I only look at the 2 centimeters, actually it represents the characteristic length scale is a lot more than 2 centimeters in the observed. And here's an example of what we estimate to be the depth of sort of characterization with the SMAP measurements. Is a lot more than 50 millimeters. Okay, so this was a topic that was of great interest. So what I would say is that, yes, we're measuring the emission depth, but actually we're characterizing a lot more in the landscape.
All right, so next is Bridget. Bridget, would you like to ask a question? Everybody?
Dara, fabulous presentation, really great job. So we work a lot with gray satellite data and looking at trends in water storage, and I prefer to focus on total water storage, but we oftentimes get questions about soil moisture input. So my feeling is that we don't see long-term trends in soil moisture, that evens out over a shorter time scale. Do you think that's true, or
in soil moisture or total water storage?
In soil moisture, I mean the contribution of soil moisture to total water storage when we're looking at long-term trends.
Yeah, I would, you know, unless something dramatic is happening, the soil moisture is a statistically stationary state variable with a very fast response time compared to total water storage, and it resets itself. You know, it's bounded between, you know, very dry, 0 almost, to porosity. So during rainstorms and during particular seasons, it can reset itself. So it can never really just be non-stationary.
Right.
Unless precipitation is
thanks.
Yeah.
Right. Thanks, Dara. And I guess I would mention that Byron Tapley said that we should be able to use the vegetation in Africa for precipitation, because they have so few gauges, and so I guess emphasizing the response of vegetation to precipitation there in the past.
Yeah, actually, with the SMAP measurements, we've tried to use it as a cumulative precipitation gauge, basically the coffee can concept, and also use it as a lysimeter. And you get, you compare it obviously with point measurements, so it's not apples and apples. You get something. I think it's a rich area to explore, to use soil moisture as a lysimeter and as a coffee can precipitation gauge. Yeah.
Thanks a lot, Dara. Take care.
Thank you.
Thank you. So Dev, would you like to ask your question?
Sure. Good to see you, Dara.
Good to see you.
Yeah, we hope things are starting to get normal here in Austin. If fall is all open and if you're able to travel, it'll be nice to have you visit us in person again and spend a much larger time. As you can see, the time we have is woefully short for the kind of questions you put. The question I have is, I mean, it sort of got answered in some sense when you talked about the length scale, but nonetheless, when we are looking at the SMAP data, it is still at the topsoil.
Mm-hmm.
There's so much knowledge that seems to be extractable out of that. On the other hand, if you look at the weather or the climate, regional climate community, we often go to the root zone as the place where the soil moisture information is embedded, if you're trying to understand. So now that we can see from soil moisture data sets coming from satellite, and there's a preponderance of that data coming through, do we need to revisit our land models? And if not, why not? And if yes, how so?
Sort of looking at it from a very high altitude, the surface soil moisture is the gateway to whatever goes on in the root zone. So nothing goes into a root zone unless it first goes through the surface. So if you have adequate temporal sampling, which we don't, but if you do, of the surface and mapping of that, I think we can infer a lot about what goes on in the root zone. And the root zone, it doesn't have a lot of the complications of the surface signal, in that it's just a damped and delayed process. And we even model it that way in our hydrologic models. In conceptual hydrologic models, the surface is becomes the root zone by just having a damping filter put on it. So, and of course we can use data assimilation, but if you want to not rely on data assimilation, I think we can't tell everything about the root zone from the surface, but I think because it's the gateway, we can tell a lot. How much is TBD?
That's why we want you to hear. We can continue discussing.
Yeah.
Thanks again. Great talk.
All right, and the last question is from Alka. Alka, would you like to ask a question? Everybody?
Hi, Professor Dara. Nice to see you again.
Good to see you.
My question is that how does the SMAP versus in situ drainage dynamics compare, especially under the really dry versus really wet antecedent soil moisture condition?
That's a great question, and I'm not sure when we look at things on tens of kilometer scale, especially with drainage, and when we look at a local scale, they can be compared. I think it's like a Heisenberg uncertainty. Your act of measurement affects what you're measuring. When you measure at a very small scale, the whole issue of diffuse and focused recharge and drainage becomes macropores, soil structure, root structure, all those. You're looking at those processes. And when you're looking at a satellite, you're looking at landscape. Yeah. I think for different applications, each one is the appropriate one. There's no sort of one is better than the other. It depends on what you're looking at. If you're looking at climate and landscapes, you want to average over all those details of roots and macropores and diffuse and focused recharge. When you're looking at a particular aquifer, then the big climate picture is no use. You need focused measurements. That's what I would say. Yeah.
Yeah, like for example, you had showed it versus the region which had the snow effect versus which didn't have the snow effect, like the Colorado Basin and the Illinois Basin. So if I'm going in that HUC regions, so in that scale also you think like that they'll be comparable or depending on use?
Yeah, I mean, in general, you know, I would say the instrument we use for each of these depends on the application. So, you know, if I'm looking at climate scale phenomena, then I want a satellite. If I'm looking at a particular location, then I need to know the conditions of that particular location. I don't think satellites should be seen as replacing in situ measurements. They measure different things and for different purposes.
Yeah.
And it's just a, you know, it's like public health versus individual medical attention. You know, you're looking at different problems and you use different tools. Yeah.
Okay. Thank you.
All right. Thank you very much, Dara, for addressing the audience questions. And thank you for your time and your interest in talk today.
No, thank you for your invitation, and I'm sorry that it had to be virtual.
Yeah, we hope everything gets better with the COVID. So thanks everyone for joining us today. I hope to see you all next week. Bye.
Thank you. Bye.
Bye.
Thank you very much. So Dara, one of the audience asked for the literature page. Can I share that page with one of the researchers?
Yeah, you can share the whole thing, but
Okay.
it's 7 megabytes if you want to, you know, depending on if they want just that one page or the whole thing.
Okay, thank you very much.
If that whole thing can be put out, several of my students and collaborators, we can just make some web page and or some location, or if you can even put it on your web page, Dara, we can just do it.
I don't really have a page.
All right.
No,
Well,
and also,
go ahead.
Sorry, for the record, you know, the recording and all that are okay. So it has to be in the end of the recording. Yeah.
Yeah, it will be published on BRO's YouTube website and on the BRO.
Yeah,
website.
we don't need to exchange emails on it, so it's okay.
Okay, sure.
So Dev, how is it going?
It's great. I think we are still in the recording mode. So if
That's okay. Yeah, I saw your interview
I think
on
it was
the radio.
Yeah, Newsweek or something. Yeah.
No, it was public radio. It was,
Oh, okay. Yeah.
yeah.
The infrastructure one.
Yes. Yeah.
Yeah. I will. Yeah. No, thanks. In fact, I will get in touch with you. I had a chance to go to and talk to the CCSP, which is a Council of the Scientific Society Presidents. And we had the NOAA chief scientist and so forth, and we were talking. And one of the things I was trying to revisit was looking at droughts and hydrology and the whole context from the infrastructure perspective. That everyone is thinking of this big infrastructure projects in the context of things we need to build, but really just rethinking things we have and how we should probably rethink those things. There might be an opportunity for some things that you just mentioned, how we should re-understand and redo things from a climate adaptation perspective. Love to hear your thoughts at some point. How do we utilize the new focus administration has and help channel that conversation?
Yeah, I mean, you know, the hydraulic infrastructure is definitely part of that infrastructure. And, you know, we've been taking things down and not building anything and repairing anything, you know.
I think we should have another conversation of
Yeah.
when the recording is not there.
Yeah,
Go into that. But good seeing you, and
Good to
please
see
do
you.
visit us. Yes.
We have a telecon with Jim Garrison this afternoon too.
Oh,
Yeah.
okay. I'll check with Jim. I will see that. Okay.
Okay, bye.
See you. Bye. Thank you.
Bye-bye.
Thank you, Sahar.
Thank you,
Good
Sahar.
seeing you.
Thank you.
Yeah.
Thanks, Deb. Bye-bye. Thanks, Bo.
Yes. Thanks.
Paul, so are you gonna take care of the recorded video?